Now, I wanted to answer a question that I posed in an earlier video, which was, how did Leonard Euler think of all these things? How did this math get invented? And where did graph theory come from? And this is an anecdote, much like with Sir Isaac Newton discovering gravity. They say that the apple fell, hit him on the head, and boom, he had the idea, okay, gravity exists or whatever. And we don't really know the truth of these anecdotes. But it's a very famous problem, which is called the Seven Bridges of Konigsberg, which is the idea of how Newton came up, how Euler came up with a lot of this math and basically developed the math that went into graph theory. So let's just go ahead and read this historically notable problem. And the problem is to devise a walk through the city of Königsberg that would cross each of the bridges in Königsberg, which were on the Pregel River, exactly once and only once. And basically, if we're looking at it, notice that there's a map over here, and we can kind of imagine what is this problem. So basically, Euler, let's just say Euler lives over here, and he is trying to devise a walk across all the bridges. Let's just say he works over here, and as he's walking to work, he wants to have like the scenic route where he can cross all the bridges. Maybe he likes bridges, I don't know why. And try to get to work having crossed each bridge exactly once. And this is kind of an idea. And you can imagine, well, how would he think of this? But he imagined a problem and he thought about solving it. And this is historically how a lot of math or physics or science gets invented or discovered anyways, is someone has an idea and thinks about, is there a way of solving this idea and what goes into that? And basically Euler developed all the math behind this. And so how he might have started was thinking about potential solutions, right? Like maybe if I cross like this way, and again, let me just draw, here's his house over here, and here's his work over there. I don't know. And again, I'm elaborating this example just to try to make some sense on the idea. But like, let's say he crosses over those two bridges from the central island, kind of back across, comes over here, and then winds up over here. But notice that if he's crossing all the bridges, like if he turns this way, the issue is, well, now he gets to this middle island, and he's out of bridges, right? And notice that if you think about the central landmass here, one of the problems, and this is what he discovered, is that there are 5 bridges that connect to that. Which, if you think about that in terms of even odd, that's an odd number. And what he notices that odd is bad, we tend to get stuck on those odd numbers. And so, if he would have gone this way instead, that's fine, he gets to work, but he would have left off a bridge. Now, he could have gone across the bridge and back, but notice that it fails the initial condition of needing to do a second bridge. And so what he realizes, okay, that setup didn't work. And then he maybe tried different setups, different this, and this. And he could have gone through every single iteration and realized, okay, there is no way to do this. And then he thought about, how can I mathematically prove it's impossible? And this is how he came up with the idea of even and odd and why that's relevant. And also what he did to try to make this more mathematical, because in that graph, there are all sorts of irrelevant information beyond it. He really also wanted to develop what would a mathematical graph look like to isolate what are the important aspects of this problem. And what he realized is that the important aspects of this problem were he wanted to travel each of the bridges exactly once. So those would be the edges in a mathematical graph, because the condition that he wanted to do was he had 7 bridges. Each one of those would be a line in the graph. And also, what connected the bridges together were the land masses. So if you're thinking about what would a graph look like, notice it doesn't really look like a street routing problem, because in the graph there are tons of streets and everything. But all of that was irrelevant information in terms of what was actually the critical aspect to the problem, which was, well, I want to cross each bridge once and have no deadheading. And basically each of the land masses are going to be the vertices. We have the northern landmass, the central island, the eastern island, and the southern island, where this would be the southern island. Notice it has 3 bridges, 2 to the central, 1 to the west. The central landmass, which is this one here, has 5, 2 to the north, 2 to the south, and 1 to the east. And then the northern has 3, 2, and 1. And this is where he developed the idea behind even and oddness of these vertices, where the northern landmass had 3, 5, 3, and 5. And now that we've already kind of discussed all of his methods, we can tell this problem is not solvable, because each of the vertices is odd, which means it has no Euler circuit and no Euler path. So basically it's impossible to either formulate a circuit or a path which crosses each bridge exactly once. And this is the problem. And so, here's a picture of Leonard Euler himself, thinking about this problem, just to be kind of goofy. But basically, we've already kind of spoiled this problem, and it took him a while to think about these things and mathematically prove them. But that's how he came up with all of these ideas. And Fleury basically just developed an algorithm, more of a computational way of doing it. But that was something that's kind of obvious to those who understand the theorems. We kind of know what to do already. And putting it into a step-by-step procedure is what an algorithm means. Just means something where a procedural process to solve a problem. And in this chapter, we're going to be learning a lot of different algorithms for solving different types of problems. And when it comes to street routing problems, what is nice is that there's only one way of solving it. Basically, if you want to find the answer, you use Fleury's algorithm. You just do the same thing every time. And there is a definitive answer, which was kind of different from the first 4 chapters, right? It was like, who should win? Well, it depends on the method. So here's the last thing in section 5.4, which I'll get to in the next video, but I wanted to kind of introduce it before we actually get into it. And the question is, well, we know there's certain cases when we're going to have an Euler circuit and certain cases when we're going to have an Euler path. But let's say we're returning back to an actual problem, like the security guard problem. Returning back to this graph here. If we apply Fleury's algorithm to try to find an Euler path or circuit, the issue is we're going to count the number of even and odd vertices. And if we look at the number of odd vertices, well, there are a whole heck of a lot, as I previously described, right? Every single one of those is all odd. All of these are odd, odd, odd. All those are odd. And if we look at this graph, there are tons of odd vertices, dead ends, degree 3, all over the place. Like, you can't go 10, you can't go 2 blocks without finding an odd vertex. And I didn't even get them all. But I'm illustrating the point, which is in a real graph, there are a lot of 3-way intersections. There are a lot of single intersections. So what do? Fleury's algorithm says, well, if you have more than 2 odds, you can't find it. So you give up. But the point is, you should not give up. How do we deal with such a problem when it is an elaborate street network and we don't know what to do? And this is what we refer to as Eulerizing. So in the last couple videos, we're going to be focusing on Eulerizing graphs because this is how we actually solve a street routing problem. And the idea is we can Eulerize a graph by adding new edges connecting pairs of odd vertices together. And this is where, if you go back to the book's video about the sweep, Euler sweep, if you play it and continue it where I stopped it in the second video, it will continue and elaborate upon this idea of how do you actually fix it and how do we Eulerize. But let's say we return back to Euler's problem and think about, well, how did Euler actually determine or continue with this process? Because what he realizes it's impossible to do it. But what he realizes is that if we were to take the Prego River, and let's say we built an additional bridge between the 2 central landmasses. What that would mean is that we would add an additional edge to the graph, connecting it like that. If we had another bridge. And what he realizes, if this were to happen, you actually could have an Euler path where he started down here and he ended up here. And let's see, well, why? Let's go ahead and trace through it. Basically, he could have gone like this, go up here, come back down here like that, come across. And if there were 2 bridges over this way, he could have went to the left, back over, and through. And he noticed that there were certain cases where it was solvable and an Euler path would work, right? And this would be an Euler path because we started at one place and then at another. And basically, he noticed that in the case when we're adding edges, what would happen is, well, notice the key problem was odd, right? Odd vertices are bad, even are good. But if I add an extra edge between 2 odd vertices, what happens is they become even, right? Because initially these were degree 5. By adding a 3rd edge, it fixes the problem and it becomes even. And once it's even, it's better. And this is the idea of Eulerizing a graph, which is basically adding edges to make it even. Because we need it to be even in order for an Euler circuit to exist. And also, let's say we wanted to Eulerize it to the point where we'd actually have an Euler circuit, we could have built another bridge over here as well, connecting the north and the southern landmass, which would look something like this. on the graph. And basically why that would help is, well, if I started down at my house and I wanted to return home, well, I could just come from work and go home like that. Bingo, that would be an Euler circuit. Basically, I'm starting at one point, um, the southern landmass, crossing that bridge, and so on, and I could hit every bridge exactly once. But basically, in its original setup, it did not have an Euler path or circuit. But if I connect all of the odds together, notice how, well, this would become degree 6, 4, 4, and 4. They've all become even, and hence the graph has been Eulerized. And that's the idea behind Eulerization. So kind of returning to the very last slide, I want to define what does Eulerize and what does semi-Eulerize mean. Eulerizing a graph is adding new edges connecting pairs of odd vertices together. So notice that how we did that is if we pair the odds together, that we would call Eulerizing the graph, we're fixing our problem, and we can solve it. And this is what we want to do with street running problems. Once it's all even, it becomes an Euler circuit. And additionally, you can semi-Eulerize the graph by adding edges to everything except for the starting and ending point. Because if we want, and basically, Eulerizing a graph means setting it up so that it has an Euler circuit, therefore 0 odds. Semi-Eulerizing pertains to Euler Path, which has to have 2 odds starting and ending point. So basically, we're not completely Eulerizing it, we're leaving 2 odd at the start and end to ensure there would be an Euler path instead. And as I said in this example, adding the red edge semi-Eulerized that graph. It left me with 2 odds. And then adding the green bridge completely Eulerized it, made it so that I actually had a full circuit. And that was an illustration of the difference between Eulerizing and semi-Eulerizing. And I'll do another video where I actually go into a more elaborate example of how do we Eulerize and semi-Eulerize, and actually find them all from start to finish.